Our bones are a marvel of natural design, continuously rejuvenating through a finely balanced equilibrium of bone resorption and new bone formation. A truly miraculous structure is formed which follows the lines of mechanical load, the trabecular bone. Sometimes, however, the unexpected happens. A drill intrudes and destroys the naturally sculpted bone. Blood vessels are torn and a major defect is created, quickly filling with blood. The titanium implant is inserted where the tooth was previously lost. At first, the only force holding the implant in place is mechanical friction. This is called primary implant stability. Oessointegration, or secondary implant stability, requires a highly complex sequence of additional biodynamic processes. This is facilitated by finely tuned communication between the main actors of wound healing, the cells. The blood immediately perfuses the surgical site, providing the cues for subsequent healing. Within seconds or minutes, ions and serum proteins such as albumin, fibrinogen, and fibronectin begin adhering to the titanium surface. Next, the bleeding is stopped by blood platelets, also known as thrombocytes. When they are exposed to collagen and other proteins from the traumatized tissue and implant surface, they aggregate and close the ruptured blood vessel. Platelets release various messenger substances for cell-to-cell communication, such as thromboxane, which promotes platelet aggregation, or PDGF, platelet-derived growth factor, which stimulates the cell division of fibroblasts. Fibrin monomers spontaneously cross-link, forming a fibrin network. The blood clot permeates the wound space, forming a provisional matrix. It also adheres to the implant surface. This blood clot has tremendous importance as a provisional matrix for subsequent bone healing processes on the implant surface. During the early stages of healing, immune cells clean the wound of the very fine bone chips, tissue debris, and oral bacteria that remain following the surgical procedure. In a first step, bradykinin from the platelets increases blood vessels' permeability. As a result, the endothelial cells move apart very slightly. On the inside of the vascular walls, endothelial cells promote the attachment of polymorphonuclear leukocytes from the bloodstream. These leukocytes, also known as PMLs, squeeze themselves through the gaps between the endothelial cells. Once they have digested the basal lamina using proteases, they are free to enter the wound. PMLs chemotactically navigate toward the wound along a molecular concentration gradient. These molecules include bacterial proteins, fibrinopeptides, and pro-inflammatory interleukins. Upon arrival, they kill bacteria through the release of reactive oxygen species. PMLs also release highly digestive enzymes such as collagenase and elastase. The wound then proceeds through an uneventful healing process, or a toxic wound environment develops with elevated bacterial counts and toxic byproducts, potentially leading to wound breakdown and implant loss. PMLs can call for auxiliary support, for example through the release of monocyte chemotactic protein, or MCP1. Macrophages respond and are the next actors to arrive on the scene. They too eliminate bacteria by phagocytosis. Tissue debris is taken up and biochemically degraded. Macrophages synthesize pro-inflammatory cytokines and proteases. Macrophages dominate during the late inflammatory phase. Using endogenous inhibitors for digesting proteinases, the so-called TIMPs, macrophages help stop the round of tissue destruction started by PMLs. This preserves the matrix proteins and proteoglycans in the wound, which in turn protect important growth factors. Messenger substances such as VEGF, PDGF, and FGF stimulate fibroblasts and angiogenesis, which initiate the proliferative phase. Fibroblasts appear on the third or fourth day. They migrate into the wound using amoeboid movements. They synthesize the protective and stabilizing components of the extracellular matrix, such as collagen, elastin, and proteoglycans. The low oxygen concentration in the tissue affects both macrophages and endothelial cells, stimulating them to create the intracellular transcription factor hypoxia-inducible factor, or HIF. Subsequently formed VEGF, in turn, influences perivascular cells. Perivascular cells are mesenchymal stem cells found on blood vessels. They migrate along the VEGF gradient into areas of low partial oxygen pressure. Here they form new blood vessels that finally integrate into the existing vascular network. Angiogenesis restores the oxygen supply and forms the foundation of bone healing. Starting around day 7, activated osteoclasts attach themselves to the fracture edges of the residual bone, resorbing it and creating space for bone healing. However, this will initially reduce the primary stability of the implant. Here, the osteoclasts dissolve the bone using hydrochloric acid and proteases, releasing BMP, TGF-beta, and PDGF from the bone matrix, which in turn initiate the formation of new bone. Perivascular cells not only create new blood vessels, they also migrate toward existing trabeculae and to the implant surface, where they differentiate into new osteoblasts under the influence of BMPs from the dissolved bone. The adsorbed proteins such as fibronectin have a crucial influence on the attachment of bone progenitor cells to the implant surface. The osteoblasts form an organic matrix that is mineralized by incorporating calcium phosphate. Under the optical microscope, bone is visible on the implant surface. Under the electron microscope, though, a thin protein layer is seen between the bone and the titanium surface. Mechanical stability is ensured by interlocking with the surface of the implant. At the end of the first week after surgery, woven bone is formed at the implant surface. This in turn promotes increasing secondary stabilization of the implant, making up for the progressive loss of primary stability. The formation of woven bone concludes the proliferative phase of wound healing. Orderly and coordinated bone remodeling restores the stability of the site. Load adaptation is of pivotal importance in this context. Initially, woven bone will have grown in the valleys of the implant surface and parallel to it. After remodeling, most bone will be structured perpendicularly to the peaks of the implant threads at right angles to the implant surface. The architecture and organization of this bone becomes trabecular. The structure is thought to be directly responsive to forces imposed through the implant to the interfacial tissues. This is made possible by the synergy of osteoblasts and osteoclasts. The osteoclasts, activated by the osteoblast messenger rankle, resorb the woven bone. The osteoblasts then lay down highly organized lamellar bone. The work of both cells is mainly coordinated by the osteocyte and its own messengers, such as sclerostin. Lamellar bone structures are formed. Similar to the arches and vaults in a Gothic cathedral, they absorb the stresses of occlusal load. We are back at an efficient trabecular bone meshwork, perfectly adapted to the new situation. Oessointegration, a highly complex biodynamic process of cell-to-cell communication, is completed.